Hey everyone, my name is Sam Eschker. I am a data scientist at Perceive. Perceive is a computer vision company based out of the IoT lab in Fishers. We use stereo cameras and 3D imaging to recognize where people are in a given space, whether that's retail, museums, or kind of other public areas. Using that knowledge, what we can do is make sure that spaces are laid out in an efficient manner, in a way that kind of optimizes for whatever the client's needs are. And in that role, something that I find that's increasingly useful is you don't always have the data to test out your different models or new ideas entirely as you would want to. One great thing that we have, though, is an ability to generate random data or random numbers that could help us do that. Something that we run into a lot also is that Python's fantastic because it has a large amount of tooling. Using NumPy and other kind of, so NumPy for doing arrays that bind directly to C arrays, or to generate random numbers using different tooling that's useful, but it's also useful to know exactly how those things work. So when you're using NumPy and you go NumPy random and then exponential variable, what are you actually doing when you're generating that number? And that's what I'm going to go through, along with a couple kind of ways that you could utilize that knowledge for different real-world scenarios. So when you're generating a random number, what you have is a distribution for that number. Everyone's used kind of the random.random number before that goes between 0 and 1, but there are other scenarios in which you might want numbers that aren't necessarily 0 to 1. You might want something that even ranges from 0 to an infinite value. One of those distributions is the exponential distribution. Now, each of these distributions has a mathematical function associated with it. What we're dealing with here is What we're dealing with here is a function that takes any given input and assigns a probability to that input. So let's say you have, at 2, you have a point probability at 2. People might get on me about there's not an actual probability that exactly 2 occurs, but we're dealing with computers and everything is ultimately discrete when we're dealing with computers. But when you say NumPy random exponential 1, what are you actually doing? What it's doing is looking at the function that would usually generate a point probability for that random variable, and it takes that function and inverts it. So you could imagine that if you say, what's my probability of the number 2, you would get a probability back for that. Now you could also say, well, given that I have a probability of, let's say, 5%, what is the number that's associated with that? That's essentially the idea when you're generating random numbers through what's called an inverse function method. This is a common method that's used for really anything where you can take a function like f of x equals e to the negative x and then flip it and say, you know what, I want to solve the other way for it, and instead figure out what x of f is. If I'm given a value of 0.8 or 0.2, how do I take that 0-1 interval and transform it into a different variable? So with that knowledge, what that means is that if you have a set of data, let's say that is a setup of pixels where you know the probability of any pixel being a certain color, what you can do is generate images from that. You don't need to train anything. You can purely use that data that's there to generate images. This can be useful for generating, for example, a data set that you're going to train over. A good example is Keith, when he was talking earlier, used a number data set. That's the common MNIST data set for random digits, or not random digits, but handwritten digits. With that data set, you're, in a sense, limited in a way where you can only know about numbers where pixels have been lit up for that number before. Much as we kind of saw with the line example where it showed up being a grizzly bear, is that if you haven't shown the model something that looks similar to what you're feeding it in when you're actually using it, you're going to have an unexpected result that comes out of it. So how do we deal with that? I'll get back to that piece. One example is when you're dealing with images, you could add random noise to an image as you're training it to give the model a kind of robustness. In this example, what I have is just a picture of a alleyway. And in that alleyway, it's every pixel actually means something. You can, instead of training a model on pictures such as this, add some noise to it. And those noisy pixels are going to add uncertainty to your model that more aligns with if you don't expect what type of images will be coming in. This is also useful if, as was mentioned over here, what if you have a different type of image, like a black and white image when you expect an RGB image? What you're going to get out of this is that, for example, you can see this is a grayscale image. There are colored dots all over it. Depending on the encoding of the image or what have you, in any kind of process where you convert that format of the image, you want to make sure that your model is not being kind of unreasonably biased toward one type of format or one style of imaging. This random noise can do that. What I did here was I read in the image using a package called Pillow. And in Pillow, they have an image object that takes each of your pixels for that image and turns it into a 2x2 array. Within that array, you can go through and operate over different pixels. What I did here was, while operating over those pixels, I added Gaussian noise to that. So I take the pixel itself, and then I have values that it can go up and down from what it currently holds. And in doing so, it generates this picture that has noise there. One big benefit of this is that instead of generating noise where you know what the pixels are, and then from there create kind of more information within it, you can instead say, no, I have a picture that's 4,000 by 4,000. I'm going to generate a ton of images that are 1,000 by 1,000 because I have all this extra information there. And then when you're running a image through that, when you take it as an input, you can run through, instead of one input image, a multitude of input images to build back in that robustness to your model. This is something very useful when you don't know, for example, rotations of images or reflections or what have you. So let's say if I was training a classifier to figure out whether this here was a picture of an alleyway, and I turned it upside down. A lot of classifiers will not deal with that well. They don't really have rotational symmetry or reflective symmetry, where if you took it and flipped it one way or the other, it would classify it incorrectly. It might tell you it's a grizzly bear or what have you. Now, in the same vein, outside of this kind of data generation, this is extremely useful for getting an overview of what's happening within your model. One example is in simulating stock prices. So this is a very kind of simple model that people can use. It's log normal Brownian motion. And what this allows you to do is say, okay, if I expect that a growth rate for a given stock is going to be 0.5% a day, so pretty quick if it's consistently growing at that rate, then what do I expect my paths to look like? You can tweak parameters in there to look at what happens if on an average day you have a stock price going up. All those are potential paths that could come out of that. And then in the case where the average stock price dips by 0.5% a day, you see it go up sometimes, down other times. This gives you a good idea of the overview, or a good overview of kind of what the model is doing and what to kind of expect coming out of it if you had unknown inputs that were going into it. For simplicity here, all of them start at the same value, but as you can imagine, there would be many different values that something could necessarily start at. Having this level of view allows you to not only pepper the space of, let's say, a stock price, but it could allow you to pepper the space of really any model that you have. So you could generate random noise or random information and then run that through your model to see what potentially comes out of it. A good example of this is something called generalized adversarial networks, or generative adversarial networks. When you're dealing with those, you will have a network try to fool the other one into figuring out what pixels are being activated the most to decide what an image should be classified as. If you add noise to that, it makes it much harder for that network to kind of fake an image. This is where, I don't know if you all have seen pictures before of, they'll take an image of Brad Pitt or something like that, and the classifier will say it's Angelina Jolie because they changed a few pixels in there that set it up to really just push the model that way. Adding noise to your input can drastically reduce the amount of times you'll have errors like that occur. So, hello? Oh. Going on from there, some of the kind of benefits of doing this is that, let's say you don't know exactly what the model is that you're needing to generate data for. You don't necessarily want to use a pre-baked version of a package that is being given to you by something like NumPy. What instead you want to be able to do is go through and check that your distribution is fitting the data that you specifically have. A couple of tools to allow you to do that are, there's great distribution plotting tools in Seaborn, which is a package in Python that lets you see across your data set what is the general kind of shape of my data that I'm getting, and am I generating data that's somewhat similar to that? One example is, I'll go back to with the exponential random variable that I talked about earlier. This here is if we use NumPy's random number generation to create a random variable. We can look at that and we can generate a bunch of points from that. But what we do want to do is check that that and whatever you do fits your specific data. Now, you can look at your data set and see if it reasonably fits also into that same paradigm. This is the graph of what the function actually is. So the e to the negative x that's going down. You can see the striking similarity between that and then when we generate our own random values for that later. You always want to do these gut checks and make sure that it's reasonable what's kind of coming out of it. So I will not kind of just go on with this. I wanted to leave some time open for questions that people would have or any discussion kind of about that. So does anyone have any questions or other things to discuss? Yep.
Hold on, wait. We need it for the live stream. We need to put you on the microphone. Sorry.
Thank you. You picked the exponential function. I guess why? Why not the normal distribution or some other distribution?
Mm-hmm. So I picked the exponential function I showed tonight mainly out of simplicity. When we're dealing with other functions, you can't necessarily find an inverse function for them. One example is the normal distribution. We don't have a closed form where we can invert that function. What you have to do instead is do other forms of simulations. One of them that you can do is kind of play off of the central limit theorem. I can go through something of kind of doing that, and then I'll explain a couple other ways that you could go through a normal distribution. So what we definitely need is an ability to have random variables. Now, the average value of a univariate random variable, so one that's just a uniform 0, 1, is going to be 0.5. Now, what you can also do is you need a bunch of values for that. So in a case where you have so here what you have is an array that I created that has 10,000 variables from the value of 0 to 1. From that, what we can go through and do is say, you know what, I want to take a random sample of 5, actually let's go to 50 values a bunch of times over. So and I'll make my step size 50 so that I can grab 50 of those. You could do a random sampling of the actual values themselves within the array, but because they're kind of randomly ordered already, it's okay to just go and loop through as that. So what we'll get is an array of arrays that are in the range of 50 values. I don't have this mirrored on my screen, so I have to kind of crane my head back for
I
each.
think this is pretty much the equivalent of a guitarist playing a guitar behind their
Yeah,
head.
it really is. It's you have to turn around the entire time. And for each of these, I'm actually going to take the mean value.
So I think this makes this demo extra metal.
Yeah. That would do it, right? Okay, now we can plot the distribution of that. And as you can see, as we add more and more values here, why don't I up that a bit? This ends up being, by the central limit theorem, a normal random variable. And so we have that generated, and the reason that we couldn't do a closed form is just that the function that is a normal random variable does not have a closed form. There's other ways that you can do this too. Another way is not by kind of going through and sampling and then taking the mean of a bunch of values, which is not very computationally efficient. You instead can use an exponential distribution, which then has the property of if you square 2 normal distributions and add them together and they're independent, it produces an exponential random variable. With that knowledge, we can walk backwards kind of from the exponential random variable to the normal one. I'm not going to go and try to go through that math because I would have to work through some of the derivation of that again to reproduce it. But in a similar vein, it was really just out of simplicity that I did the exponential random variable, but also it's very useful because you can use it for things like normal generation. And then from there, if you have a log normal random variable, that's really just e to whatever the value was for your normal variable. So they all connect to each other, which is kind of a beautiful thing in that we have the ability to walk between any probability distribution that we have purely. If we're able to generate it on a computer, that means that we had a way to analytically go from one distribution to another. It's from that mapping to the 0-1 interval, which in other terms is looking at the inverse of your cumulative distribution. And so it's a very kind of powerful thing that we have there. Another kind of piece that comes off of that is that you can, instead of in the case of sampling a bunch of times to get a normal distribution, you could sample a multitude of times to get really any distribution that you need. So let's say that you have a lot of words, so a corpus of words. And that corpus of words, you can look at one word and then the word that comes after it. Let's say that there's meaning in that. You can assign a probability to what word comes after it, but something to keep in mind is that it's only as smart as the input data that you give it if you do something of that nature. For example, if you walk backwards and you gave a algorithm a bunch of text and then asked it to figure out what the word before Eschker was, it'll probably come up with me, my sister, and my parents' names, and probably not very many other people's names. And that's just because you don't have kind of the amount of data going in there. What you can do, though, is have, in that case, taggings of words and then randomly generate text or randomly sample text to provide some randomness that comes in. Jason was talking about the situation where we have an essay that's being written. Really what we are as people is, in a way, imaginatively random. So we come up with things and we'll produce new sentences, things that we think we haven't heard before, but they're ways that our brain has put together a kind of a random selection of words that we have a already pre-existing knowledge of. When you look at what comes out of an algorithm, it's going to be kind of a similar output, minus a few pieces. There are certain details in that, like they'll generate hundreds of essays, read all of them, and then choose the one that is most reasonable, which you're always going to kind of run into situations like that. But yeah, I hope that answers your question.
Yeah, we have plenty of time for more questions.
Yep.
We've got about 10 minutes, easy here. More questions for Sam?
Yep.
Yeah, let me hold on one sec. Coming your way.
For the purpose of this noise for testing, are cryptographically secure random number generators better than the simpler random number generators?
So this is a really interesting topic. One is that it's actually not clear what a cryptographically secure pseudo-random number generator is. There are truly random number generators that deal with kind of atmospheric data or other things like radioactive decay or things that we kind of view as being entirely random within our physical world. Then there are the other random number generators that deal with taking a number, raising it to a very high power, kind of modding that in some way, and working through a sample space to then produce back a random string of bits. Unlike in the situation where you have cryptographically secure hashes or functions of that nature, there are clear boundaries around tests that those need to kind of go through in order for the algorithm to be certified as such. For example, SHA-256 or MD5 or an algorithm like that needs to go through a series of rigorous testing where they try to find collisions between hashes in some type of trivial way or even non-trivial way that could be computed in a reasonable length of time. With random number generation, the tests are less clear. It's not quite as easy to say, oh, well, I generated 1 million numbers. Is that reasonably similar to a distribution? There are ways to test how similar one distribution is to another, but they kind of fall apart when you generate a lot of numbers. The reason for that is they focus around adding up different differentials. So they look at what should the distribution be and what is the distribution that came out of these numbers. When you have just, let's say, millions of numbers that you've generated, those differentials add up so significantly that almost any way that you would test that, so in a very small case like a chi-squared test, those tests are going to have statistically significant results in nearly every scenario. And that makes it very tough to kind of check. The good answer is that you need something good enough for your use case. If you're deciding on how you want to generate your random numbers, there are ways to do it that are accepted by like a lottery or ways that would not be accepted by a lottery organization because they're not considered random enough, or you can maybe guess a seed or whatever it is. Fun story, actually, about that. The normal algorithm that's used to generate SSH keys on all of our computers, there's maybe about 0.5% of those that are collisions between computers because the algorithms seed the same way. And so your private key, there's a decent chance that it actually is shared by someone else in the world that has that exact same private key, even though it's generated with a cryptographically secure function. What comes from that is that it was a function that was given an input, and they try to make that input as random or unpredictable as possible, but sometimes it just isn't, and it gets initialized with the same value. If it's initialized with a date, it might be January 1st, 1970 on a ton of computers, or whatever it might be. So that's, it's unclear is the best answer.
So to avoid that, what do you do?
I mean, you could choose something cool about your life and then seed it, or you could go to a true random number generator that uses like physical noise and use a number coming out of that as the seed for when you're generating your keys.
Cool. All right. More questions?
Kind of to add to that answer, really, you can use a cryptographically secure random number generator for machine learning applications, but there's no point to it. What really matters is the statistical distribution. But inversely, for generating keys, simply because you're using a quote cryptographically secure random number generator may not be quite as simple as it seems. Like using, in particular, physical noise sources can be really problematic because they don't have enough entropy. So you can maybe use it to whiten an existing, or to apply a cryptographic PRNG to seed and then random and then add noise to it with the physical source. But it's really two completely different applications. So machine learning, there the statistical properties are important. But the fact that you can't distinguish statistically the output of a random number generator from randomness doesn't mean that it's cryptographically secure.
Any other questions for Sam? Oh. One from the back.
Yeah, so I recently had a chance to sit with really an IoT group of a pretty prominent law firm. And one of the things that they suggested was that one of the fastest growing pieces of their tech practice is IP of algorithms and models in a way that transcends really anything they've seen in the past. Just how would you describe what's really out there for the hacker, the amateur in my case, versus what perhaps the more astute piece of the industry is approaching, pursuing?
So I'm not a lawyer, so I can't necessarily speak to all the little legal aspects of case law that go around.
But do you play one on TV?
No, I do
Okay.
not. That'd be fun though. One thing that I can say is that from what I've gathered, you have to show that you're using something in a specific context, using a certain tooling in order to then claim it as IP, and you need to protect it continually. With math, certain math concepts, that's going to be nearly impossible to do. Mainly because there are so many programming languages that you could program something in. Does it compile down the same if you program it in two different languages? Probably not. The instruction set to the computer is probably going to be different. So what are you actually kind of protecting in that nature? So there's trade secret that goes into different algorithms being used. One thing though is that there's a lot of this research happens in academia also that then gets utilized and expanded upon for use in industry. And given that kind of knowledge that's out there, a lot of the times another company probably wouldn't even benefit much from stealing certain things from you. There are certain pieces of knowledge that your company has that could be the key to you being much, much better than your competitor. There are other areas where the use case is so specific that you have built it around your data structures, your kind of inputs and outputs, where your clients' needs are, and you've made changes to models that you read in a math paper somewhere that make it useful for you, and it makes it less useful to someone else when you make it useful for yourself. So I can't answer from any kind of legal perspective, but I know in practice, models change a lot when they change hands, and that makes them pretty hard to kind of nail down and say, no, this is exactly it, and I'm going to make sure no one else does it.